The class coNP, there is a subtle way of taking the complement of a complexity class. It is given by the following definition. Definition 18.10. We say that the language L is in coNP if there exists a Turing machine T and a positive integer k so that the following hold. For each x not in L, there exists a witness w of x so that when T is given input x w of x, it will recognize that x is not in L in big O of n to the k time. For each x is in L, no such witness exists. That is, no matter what input x w prime of x we give to T, we cannot trick T into falsely saying that x is not in L. In other words, coNP is the class of languages for which we can verify non-membership in polynomial time. The following is a classic example of a naturally defined problem which is easily seen to be in coNP but requires more work to be seen in NP. Example 18.11. Let primes be the set of all prime numbers, then L is in coNP. Solution. Let x be the integer for which we want to show that x is not in primes. A proper divisor d equals w of x can play the role of witness for x is not in L. Indeed, then T can simply divide x by d and verify that there is no remainder. If x has n digit, then this can be done in big O of n squared time. Note that as we said before, n must be the size of the input, that is, the number of digits of x. Therefore, the following argument would be wrong. The language primes is in P since we could simply check for each integer I satisfying 2 less than equals to I less than equals to the square root of x, whether I divides x. This takes square root of x steps, which is less than a polynomial function of x. The problem with this argument is that we need an algorithm that is polynomial in terms of n, not in terms of x. The reader may ask why we defined coNP before defining coP as the set of languages for which we can test non-membership in polynomial time by a Turing machine. We encourage the reader to spend a moment trying to figure that out before reading further. The answer is that coP equals to P, since if T can test for non-membership in L in polynomial time, then the same T can test for membership in L in polynomial time by simply interchanging the accepting and rejecting states at the end. This line of thinking leads to the following proposition. Proposition 18.12. We have P which is a subset or equals to NP intersect coNP. Proof. On the one hand, proposition 18.8 shows that P which is less than which is a subset or equals to NP. On the other hand, by the same argument, coP which is subset equals to coNP. As coP is equals to P, our claim is proved. We would like to point out that it is somewhat more difficult to prove that the language L, consisting of all prime numbers, is in NP. That result is called Pratt's theorem, and it can be proved using very enjoyable facts from number theory. In fact, the following characterization of primes can be used. An integer p which is greater than 1 is prime if and only if there exists an integer r, so that 1 is less than r less than p and 1 r to the p minus 1. Then minus 1 is divisible by p. 2. If q is a prime so that q times d is equals to p minus 1 for some integer d, then r to the d minus 1 is not divisible by p. Even p and witness w of p equals to r for the primality of p, a Turing machine can verify in polynomial time whether r indeed satisfies the requirements. It is even more difficult to prove that primes is in p. That is perhaps the most celebrated recent result in complexity theory. The proof by Aguaro, Kaya, and Saxena was published in 2004 and takes only 12 pages. It is also worth pointing out that 2 of the 3 authors were undergraduate students at the time the proof was found. The non-containment relations between the 3 complexity classes that we have defined so far are shown in figure 18.1. The non-inclusions between the 3 complexity classes defined so far. At this point, you are asked to test your understanding of the concepts of this section by proving the following proposition. Proposition 18.13. The following 2 statements are equivalent. 1. P is equals to NP. 2. P is equals to coNP. We end the section by noting that it is not even known whether NP is equals to coNP. It is widely believed that these 2 classes are different, just as it is widely believed that P and NP are different.